Welcome to No Worries Biology. My name is Anja Doyle, and today I would like to talk about the chi-square test as a tool in statistical data analysis. In statistics, the letter chi, more precisely the lowercase chi, has a number of meanings and functions. In our case, it gives the name to a mathematical algorithm which is used to evaluate the significance of collected data for a scientific hypothesis. The chi-square test uses a mathematical formula which we are going to have a look at and discuss in just a few minutes. It uses this formula to compare experimentally collected data to statistically expected data, and it evaluates whether the discrepancies between both sets of data can be explained by mere chance, or if the discrepancies are large enough to indicate that the hypothesis underlying these statistical expectations is incorrect. Therefore, the chi-square test creates an objective mathematical basis for accepting or rejecting scientific hypotheses. At first glance, this might sound quite abstract and complicated, but no worries, it will become much more accessible and understandable when we look at a specific example. Imagine a friend comes and visits you, and this friend tells you about a game of dice he participated in the previous night. Your friend confides in you that he didn't do so well. It might just have been about a really bad luck, but your friend suspects that the die might have been loaded, meaning influenced in such a way that it doesn't roll randomly anymore like regular dice. Your friend values your expertise and diligence and therefore asks you to investigate this matter. And for that reason, he has even brought the die in question with him. First of all, you thank him for his trust, and then you think about how to approach this matter. You start by posing your void hypothesis, the so-called Null Hypothesis. Because loaded dice are rather rare in the real world, you assume that the die has not been tampered with and that your friend has just been out of luck last night. So your Null Hypothesis has to be the die is fair, therefore the alternative hypothesis has to be the die is not fair. How can you now check whether your hypothesis is correct or not? To answer this question, it is important to point out that a null hypothesis always has to be phrased in such a way that you can come up with certain statistical expectations for it. So in our example, the die has 6 sides, each showing a different number of eyes between 1 and 6. If you were to roll that die 600 times, it is reasonable to expect each number of eyes to come up 100 times. This is our statistical expectation. Diligent as you are, you now sit down and actually roll that die in question 600 times in reality. And while you're doing so, you're carefully recording your results. Subsequently, you compare your expected results to the actually observed results. Some might be a bit higher, some might be a bit lower. Now you need to evaluate whether the differences between the observed results and the expected results can be explained by chance, or if chance is not enough and the die has been manipulated. This is where the before-mentioned formula for chi-square comes into play. It says chi-square equals the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. Using the data table we have already created, this is easy to do. We start by subtracting our expected frequency from our observed frequency for each number of eyes. 111 minus 100 equals 11, 90 minus 100 equals minus 10, and so on. Then we raise each of these results to the second power and divide it by the expected frequency. And last but not least, we add the results of all these lines together, because this is what the sigma sign, the sum sign, means. And there we have it. The value we calculated for chi-square is 12.26. So what does this figure tell us now? Nothing by itself. To give it meaning, we need to compare it to the critical values provided in the chi-squared table. But before we can do so, we need to discuss two more aspects. The first is the so-called p-value. P stands for probability, so it is the probability value. This value indicates how certain we are that our evaluation of the data is correct. Life rarely gives you 100% certainty. So it is also acceptable to be 99% or 95% or even 90% certain. A p-value of less than 0.1 indicates that the likelihood of our evaluation being wrong is less than 10%. In other words, we are 90% certain that our evaluation is correct. A p-value of less than 0.05 translates to a likelihood of our evaluation being wrong of less than 5% or a certainty of 95%. And a p-value of less than 0.01 indicates a likelihood of our evaluation being wrong of less than 1% or a certainty of 99%. In biology, a p-value of 0.05 is used most often. A p-value of 0.1 is often used in social sciences, and a p-value of 0.01 is used where it is necessary to work very, very accurately. We are going to work with a p-value of 0.05. The second aspect we need to talk about are degrees of freedom. In statistics, degrees of freedom are used to indicate the number of categories the results can fall into. Our die has 6 sides, each with a different number of eyes. So whenever you roll the die, you would expect one of these numbers of eyes to come up, one of these categories to come up. If each side of our die would show exactly the same number of eyes, then you would know the result before you even roll the die. Each result would fall into the same category in this case. That can't be called freedom at all. This is why in order to determine how many degrees of freedom you're dealing with, you need to subtract 1 from the number of categories that is possible to achieve in your results. With our die, we have 6 categories because we have 6 different numbers of eyes. 6 minus 1 is 5, so we are dealing with 5 degrees of freedom. Now we are ready to look at the chi-square table. Here are the degrees of freedom, and here are the p-values used in biology. Because we said that we would work with a p-value of 0.05 and we have determined that we're dealing with 5 degrees of freedom, the critical value applicable to our set of data is 11.07. Now, whenever the value determined for chi-square is larger than the critical value provided in the table, this means that we need to reject our hypothesis. In our case, chi-square equals 12.26. This value of 12.26 that we have determined for chi-square is larger than the critical value of 11.07 that is given in the chi-square table for 5 degrees of freedom and a p-value of 0.05. Therefore, our null hypothesis that the die under investigation is fair must be rejected with a certainty of 95%. In other words, we can tell our friend that the data we have collected from rolling the die differs so much from the data that is statistically to be expected that we are 95% certain that the die he had been playing with last night had been tampered with or was loaded. Wow, next time you should play with somebody else. Let's have a look at a second, somewhat more biological example. When Gregor Mendel conducted his pea experiments in the 19th century, he expected dominant traits to appear at a ratio of 3:1 over recessive traits in offspring of heterozygous parents. Today we illustrate his hypothesis like this. We are investigating the shape of peas, round dominant versus wrinkled recessive. Our parental generation is heterozygous, meaning they are possessing both alleles, the one for round and the one for wrinkled shape, but they themselves are round because that is the dominant trait. The parental generation produces gametes, reproductive cells, which each only contain one of the alleles, and during fertilization those gametes each combine with a gamete from the other parent so that the offspring again possesses two alleles. The following combinations are possible: homozygous for the round allele and also phenotypically round, heterozygous containing both alleles and phenotypically round, heterozygous containing both alleles, phenotypically round, and homozygous for the wrinkled allele and phenotypically wrinkled. So phenotypically, in their outer appearance, and that's the only aspect that Mendel was able to observe, 75% of the offspring should be round and 25% of the offspring should be wrinkled. That is our statistical expectation. In his paper Versuche über Pflanzenhybriden, Experiments on Plant Hybridization, Mendel offers, amongst many other sets of data, the actual results of this crossbreeding scenario conducted with 10 different plants. When adding these numbers together, we have 336 round seeds and 101 wrinkled seeds in an overall number of 437 seeds. Projecting our statistical expectations to this overall number of seeds, we would expect to see 327.75 round seeds and 109.25 wrinkled seeds. So the observed and the expected frequencies are similar, but are they similar enough to support Mendel's hypothesis? When we apply the chi-square formula to this scenario, we end up with a chi-square value of 0.83. There are two different categories the results could have fallen into, round and wrinkled. 2 minus 1 equals 1, so we are dealing with 1 degree of freedom. The critical value provided in the chi-square table for 1 degree of freedom and a p-value of 0.05 is 3.84. Our value for chi-square, 0.83, is much smaller than the critical value provided in the chi-square table, 3.84. Therefore, with a certainty of 95%, we can say that the data Mendel collected in his pea experiments supports his hypothesis. This example also illustrates another important aspect to keep in mind, namely that the amount of results or of data that are collected should always be sufficiently large in order to balance random variations. If, for example, we would only have had the results of one of the plants Mendel mentions as an extreme, where he found 45 round and 2 wrinkled seeds in one plant, then we would have calculated a chi-square value of 10.14, which would be much larger than the critical value, and therefore our conclusion would have needed to be that Mendel's hypothesis was wrong. Similarly, this also applies to the die example. It does happen occasionally that you roll a 6, for example, 3 times in a row. And then it's very easy to get the feeling, something might be off here. But it is very, very unlikely that you roll a 6 100 times in a row, or even 600 times in a row. This is why in our die example we needed to have this very large amount of die rolls in order to determine whether or not the die was fair. In conclusion, we can therefore say that with a sufficiently large data set and diligence when applying the chi-square test, we are able to evaluate whether deviations of experimentally collected data from our expectations can be assigned to mere chance, or if the hypothesis that led to our statistical expectations must be rejected. That's it for today. at www.noworriesbiology.com. You can find a ton of materials on many aspects of biology. Just have a look around and maybe there's something that you like. See you next time.